Nice. Let's make it run straight into some minifigures. It spotted them. It's turning away from the minifigures. Hi there, I'm Anton from Anton's MINDSTORMS Hacks. In this video I want to talk about Gelo. Gelo is a robot that was included inside the LEGO MINDSTORMS set, and what I've been doing is I've worked hard to make Gelo move in a really natural way. The problem is we have a curfew here in the Netherlands and you can't go out after 9 o'clock, except if you have a dog. So I've been working hard to make this dog walk and look like a real dog, so I can go outside and no cop will stop me with this thing on a leash. The first thing I want to do is program Gelo in the simplest possible way, that is with the MINDSTORMS word blocks, or Scratch as you call it. Programming Gelo this way is pretty simple, but it doesn't look quite natural, and it nobody will believe me if I have to let a dog out that works like this. So the way to program it with word blocks is to go to the extensions. So the extensions are down here, and go to model blocks, add the model blocks. Once we have the model blocks down here, they are red blocks. We can have a look at the Gelo blocks here. So we could say set Gelo's speed to 50%. That's easy for the video. And then get Gelo into position for walking, and then walk straight for a few seconds, and let's see what that does. Okay, it's downloading. There we go. Okay, you see that Gelo puts every leg in position individually and then starts walking. The walk is okay-ish, but it could be better, and the positioning of the legs is a bit shaky. If I would have to combine that into a turn, then so if I want Gelo to turn afterwards, I could, I don't need to reset the speed. I put him in a turning left position, and then I make him turn left, and let's see what happens here. It has to reset its legs every time. Downloading, it resets the legs, then it starts walking. It completely stops, resets the legs again, and starts turning. This is a pretty unbelievable motion for a dog on the street, so let's try and improve that. To improve it, we'll just use some Python code. What I've done is I created a boilerplate Python code. I don't know why they call it boilerplate in programming language. I'm not going to build any boilers, but boilerplate code means it's a piece of code that you can use as a base for your new programs. So let's go to my website and get this boilerplate code. Here we are. This is my website, antonsmindstorms.com. I just recently installed a caching plugin. It's very fast now, and so I'm a bit addicted to the reload button. But anyway, the article we're looking for is called Python Motor Synchronization. Let's click that. Awesome how fast that loads. So I'm really happy with the caching here, and I advise you to read all of this because I put a lot of work in there, and if I'm going too fast in this video, this will give you some background information. For now, you can scroll all the way down. This is where the boilerplate code is. So let's copy all of that. Scroll, 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 scroll. And there we have it. This is some basic code that you can use into your MINDSTORMS program. Now we're going to make a new Python program. There we go. Python. And paste all of it. Now, what we have here is boilerplate code, and we'll just start simple by programming the, let me show you on the model, the front left leg here, and we are going to call it FLL, not for first Lego League, but front left leg. I'm a little lazy, so I use very short variable names, FLL, and FLL is going to be hub.motor.port. Oh, that's wrong, hub.port.d.motor. So this is a hub style definition of motors. Maybe you're used to this definition of motors, but this is actually a wrapper around the core firmware, and the core firmware sees motors like this. So we haven't imported the motor class up top here. See, there's only hub, utame, and math, and so we're going to stick to that and use the deep layer firmware hub.port.d.motor objects. Next, we need a function that will return a position for our motor at whatever time we put in, and I want my front left leg motor, let's make it a funky function, func, and I want it to be a linear function, and I want it to run 360 degrees per 200 milliseconds. And now we get to the part here with the meta function. So linear, this is a method that I've provided, it's up there, and the funky thing about this function is that it returns another function. So inside this method, it defines a new function and then returns that. This means we can now, this is not a variable, but it's an actual function, and we can call it like if we would have defined it. So we can call it like this, let's say 2000, and this should return 360 because I want it to run 360 degrees per 2000 milliseconds. So let's print this and run it and see if that works. Okay, it worked, it returns 360. Now this is a bit boring, nothing is moving yet, so now we'll make it move. So we are going to make it a while true loop, and oops, oh, that was a little too fast. First we need to define our mechanism. So let's say our list of motors is a bit of a sad list, it only has one motor in there, and our list of motor funcs, keeping it funky, is a bit short list. It has only the FLL func in there, but now we can define a mechanism, and let's call it walk straight, because that's the first thing we're going to try with Gelo, and it's a mechanism, and it has motors and motor funcs. See, so I'm creating these two lists with only one item, but this mechanism class needs a list of motors to synchronize, of course. Synchronizing one motor would be a little sad. And now that this mechanism is defined, we need a timer too. So let's create a timer here. In programming lingo, this is called instantiate. To instantiate a timer, to instantiate an amazing hourglass timer, an Anton's MINDSTORMS timer, and it doesn't need any arguments. So now we have a mechanism object and a timer object, and in infinite loop we can update our motor powers, and as an argument there we are going to use time. The cool thing about this timer, by the way, is that it can make time run backwards, faster, slower, accelerate, everything. So this means that in this control loop we can also make Gelo accelerate. But that's something for later. Let's see if we made any programming mistakes, and Gelo starts walking. This is not a walk yet, of course. This is as expected. But what we see here is that our front left paw, front left leg, does a nice smooth revolution. It takes about 2 seconds. It takes exactly 2 seconds to make a full movement here. So now we have one leg working. Let's see if we can synchronize the other legs to that. Now we have one leg, one function. Now, let's maybe add the other front leg. Front, right leg. Furl, furp, or whatever. The front right leg, I believe, was motor C. Port C motor, and it needs a funky function. Let's give it a funky function. Furl func. Furl func is also going to be linear, and we also want it to run. Actually, let me switch to the model. Actually, what you see is that these motors are built in mirror fashion. So I'll probably have to run this motor backward while this motor runs forward. That's pretty simple. With this setup, I make it run -360 per 2000 milliseconds. Now I'm repeating this number here twice, and in software development there is a adagio: keep it dry, do not repeat yourself, DRY. So we can make this code a little drier by making a constant of this number. This constant is going to be called period, period, period. We're going to make a constant period. No, period is actually a word in wave theory where it is the time span in which stuff starts repeating itself, or you could call it loop time. I'm just going to call it period. And the nice thing about this is then I can later lengthen or shorter the period to speed it up or slow it down. Now we have a furl and a furl func, and we have to add our furl to our list our motors and our furl func to our list of functions. There we go. This is the same, this is all of the same, and all the rest stays the same. Let's see if that works and if we didn't make any programming mistakes there. Okay, it does something. It's synchronized. That's cool. If I hold one leg, it will really work hard to keep both legs synchronized, even so hard that it breaks itself. But this is not a walking motion. It's more like scratching the dirt. So what happens is that these motors are now perfectly in sync, but I have to offset one motor a half a turn to make sure that it's more like a pawing or a walking motion. Let's stop the code here and try and do that. So the other leg here, it needs an offset. Let's give it an offset of 180. So that's the nice thing about this linear meta function. It now creates a new function with this exact offset. Actually, I could show here on my iPad what we're doing. Okay, what we have done now is created two functions. So I'm going to draw a diagram here with time t, and our first linear function was pretty simple. It's linear, so it's a straight line, and we asked the function to after 2000 milliseconds or 2 seconds to be at 360 degrees. Now our first try with the second motor was just straight the other way, and it was at minus 360 and so on and so on, and it kept perfectly in sync with the other motor, but this was not the movement that we wanted. So now we're going to scrap all that and create a new function with an offset of 180 degrees. So it's going to cross my y-axis there at position 180, and this means that every time this motor, the blue motor, has run a full turn, this one will have only run half a turn, and also it will have run the other side in the other direction. And it starts, of course, at 180. So this is the way to think about the mechanism in function style. So let me add some notes here. So this is the front, our FLL, front left. And the brown line down here is our front right. So this is what I did. I gave the front right leg an offset of 180. Let's run this code. Ain't that a beauty? So now we have both legs running in the right direction with the right offset, and it works hard to keep it in sync. If I put the model down, it will walk a little, but it will drag its hind feet, and this is not a nice walking motion. So let's stop that. And now it's quite simple to add the other legs. So let's add more legs here. We have a hind left leg, back left leg, hind, I think hind. Hind is, I think, the right English word. I'm just a Dutch guy trying to speak English here. Ooh. Our hind left leg is hub.port. It's behind the D, so that's where B is, if I'm remembering well. And nope, just a motor. And our hind right leg, hurl, is at hub.port.a.motor. Checking on the model, looks good. Now we need two more funcs. So let's copy all of this funky stuff and change the F's into H's. Now, okay, now let's think it through. The front left leg runs forward, so that's a positive number. And the hind left leg is in the same way, so it should also run forward. So this part is right. However, two legs on the same side of the robot should have an offset, so they aren't touching the ground at the same time. So let's give this guy an offset here. Offset. And since our front right leg already has an offset, we'll remove it here, so they effectively have an offset. Because if I give them both the same offset, they run in sync again. That's not what we want. So we have a functions. So we have 4 functions here to define the positions of our 4 motors in times. So now let's expand our list with these motor functions. Hole and hurl. And of course, funk, and hurl, funk. Okay, there. And the rest of it stays the same. Let's have a look. See if we made any mistakes. Da, da, da. Coolness. It's alive! I have to stop it because this one keeps going on forever. To demonstrate how this works and one number is connected to all motor positions, I'm going to use this crankshaft. So let's see how this crankshaft looks in code. Create the crank here, cranky, cranky, let's call him cranky. The cranky crankshaft. Cranky is hub.port.e.motor, and we are going to use cranky's position. So degrees counted is cranky dot get, and the thing is cranky dot get gives us 4 numbers and we only need the second number in that list, so we are going to use a Python index here that gives us the second number. 1 gives us the second number. 0 index would give us the first number, and degrees counted is the number that we need here. I have another article on my blog where I detail all of this get and this hub style definition of motors. So instead of timer, we are going to use the degrees counted of our the cranky crankshaft motor. Switch over to the model. Forward E. Okay. Run the code for the cranky crankshaft. Ah, we made a mistake. Ah. Let's see what our programming mistake was. Oh, it says Harl Funk. I don't know how that mistake came in here. Somehow one of these functions became a motor. Okay, let's try it again. This is more like it. Okay, cranky crankshaft, do your work. You see, so whatever number is generated here from the crank, the motors try and move to that position. And the funky thing is I can run the crank backwards and the motors will try and reach that position. I have to run it real fast because our period is pretty long. I could decrease the period and make it go faster. So let's try that just for laughs. Okay, so we decrease this. We make it go really fast. This will give us much more leverage on our crank. Yeah. See? Cool. This part of the mission is done. We have synchronized motors in Python. And one thing I don't like is that before it starts walking, there is a little jump. And to program around this, I have created a method in the walk straight class, and I think it was called reset something, shortest path reset. So let's go shortest path reset, and this will put all the motors into starting position before we go. Let's remove the cranky crankshaft here, timer time, and we're not going to run all the time, but we are going to run only for 3 seconds. Okay, this one resets all the motors at the same time, and unlike the scratch, this will do them all of them in parallel and not individually. Let's take a look at this. Oops! I don't like the shock it does. Ah, I see what my problem is there. The shock is created because I instantiate my timer and then I reset the legs, and then the timer is already running without the robot running. So I have to make sure that I create my timer just before the loop, or at least I reset it just before the loop. But I'm going to be lazy and create it just before the loop. Okay, let's see how this runs. Awesome. So that's a very smooth start and a nice controlled walking movement. Let's run that again just because it looks so cool. So that's a smooth start, and now it starts walking smoothly. Okay, then our next step is we want the dog to walk around the room and sniff around the room like a real live dog, so we'll also have to make it turn. Let's try and make it turn in with these mechanisms. Turning is the same as walking straight, but it just takes different functions. So these are actually the walking functions, and for turning, what we have to do is run one side of the dog in reverse. So let's create the new list of functions. So this is actually the motor walking functions, and let's create all the turn functions like this. So this is front left, front right. I'm going to reverse, let's say I reverse the right side, so I take this, and this is also a right leg. I remove this minus. So these, now the legs run in opposite directions, so everything is positive. They still have their offsets, and I think this will generate a turning motion. Let's put this here, put this there, motor, turn funcs, and make sure that we add the turn thing in there. Turn through the ring of fire. No, let's burn. Okay, so we have all of our turn functions. The list of motors, we could move it up there for clarity. And so we have a walk straight. We walk straight for 5 seconds, and then we stop, and we could do just the same. And we could have a turn is with the turn functions, motor turn functions. Where is it? Motor turn functions. Motors, motor turn functions. That's the mechanism. And here is this mechanism. So this is a new mechanism. I'm going to call it turn, and it has motors, but it has turn functions. I'm going to reset it, reset the timer, run the time, and see if our dog starts walking. And of course I have to stop the turn there. See if this, if I've done everything right, they should walk the dog straight for 5 seconds, and then make it turn for 5 seconds. Let's have a look. Oops, mistake. What did we do wrong? Line 257, motor funcs. Oh, I renamed it. I should have made this motor walking funcs. Okay, that happens if you rename stuff. Let's have another try. This is better. Okay, walking 1, 2, 3, 4, 5. 5 seconds is over. Prepare to turn. And it's turning. It's turning right. Cool. So now we have a walking and turning dog. The walking and turning dog is nice, but this is a pretty short program. It would be cooler if it would actually watch its distance sensor and walk straight until it sees an obstacle and then turns for some time and then walk straight some more. In our current program, it's pretty simple to add, so let's go ahead and add that bit of code. Okay. What we are going to do is to put all of this into a loop, and we are going to infinitely, forever switch between walking straight and turning. The walking straight is turning for 5 seconds is okay. It could be maybe a little longer. And turning, we're not going to stop turning after a certain time, but when the distance sensor sees a certain distance. So let's go here. Distance is less than I don't know, 10 centimeters. Now distance is a function that I just made up here in our while loop. I still have to define it. So let's define our distance function here. Cranky is gone. We are having a distance sensor in hub.port.e.device. Okay, and what we are doing here is distSensor.get. Distance is distSensor.get. The problem with this is that actually there are two problems with this. I run into this so often. This thing returns a list, and it's a list with one item, but still we have to unpack it to find the one value in there. So we take the zeroth, the first item in that list. Then there is another problem. If the sensor doesn't see anything, it returns none. So that's not a number, and if we want to compare distances, that will get us into trouble. So we have to check if distance is not none, if it's returned. So if there is a distance, it's not none, then we return that distance. If there is no distance reading, or it is 0, we will return a large number. I think 200 is the default, so we're returning the same thing there. And then there is another problem with the distance sensor if you run it in tight loops like this, where the motor voltages are called all the time. My experience is that it doesn't update right. So well, you could try without, but I like to use a wait for seconds. And let's wait about 50 milliseconds, and then only then read the distance value. Now, wait for seconds is something that we haven't imported yet. So we could import this here from MINDSTORMS.control. Come on, import wait for seconds. Okay. It doesn't wait 4 seconds, it waits for seconds. It waits for seconds, 0.05 seconds. And now this method here, distance, will return a number that I can safely compare to another number, and it won't crash if it returns none. Let's see if we programmed everything right and we haven't made any mistakes. Okay. It starts turning right away, so apparently... That's a stupid mistake. Okay. Stop it. Of course, it should run forward while the distance is more than 10 centimeters. Classic mistake. Try it again. Okay. Nice. Let's make it run straight into some minifigures. It spotted them. It's turning away from the minifigures. Halt! Don't eat the podium, doggy dog. Okay. Halt! There is a podium. Okay, so this dog will now walk around your room, and it will spot spectators. So it has spotted our brave spectators over there and has turned away. It'll spot new brave spectators, turn away, and walk around the room all day. Okay, so this is a pretty lengthy tutorial, I think, but the basic concepts are pretty simple. So what we did here, to sum it up, we defined our motors, had the port style. Per motor we defined functions, and depending on the movement that you want from your robot, you have a different list of functions here. And we also saw how to read from the distance sensor without getting the error if you compare none to an integer. And then here in this while true loop, you can see how we change the movement between walking straight and turning, and it's all dependent on our distance reading here. If you, on my website, there is more in-depth information about how all of this works. So I encourage you to check out this code, how it works. I try to add as many comments here as possible. The mechanism, how it's defined, how the update power works. Okay, so this concludes the tutorial animating Gelo in Python. I hope you enjoyed it, and I'm looking forward to seeing all of your legged walkers and all of your nice Gelo movies. Thanks for watching. Please don't forget to subscribe. So please subscribe to my channel, so You will be notified of updates. In a next video, we will go more in depth with Gelo. And what we did right now is a linear function. So the time that a leg spends on the ground is the same time as it spends in the air. And if we make that non-linear, we can make the leg stand on the ground for longer and then really quickly go through the air to make another step. And this looks even more natural as a movement, but that's a bit more complex to program, and I'm going to do that in a different video. So again, thanks for watching. Subscribe if you really like these kind of videos. It also helps if you support me on Patreon. The more supporters I have, the more time I can spend on this video making hobby. Thank you. Bye bye.